Section 3.6, curve sketching. Concepts you have learned for analyzing the graph of a function. X and Y intercepts, symmetry, especially even function, f of negative x equals f of x gives us y-axis symmetry. Odd function, f of negative x equals the opposite of f of x, origin symmetry. Domain and range, continuity, vertical and horizontal asymptotes, differentiability, relative extrema, concavity, points of inflection. All of these things you have learned, and they will help us to sketch a graph that you don't have any idea how that graph looks. Remember, when you sketch the graph of a function, you do not normally show the entire graph. You want to show the parts of it where interesting things are going on, such as the items above. Guidelines for analyzing the graph of a function. 1. Determine the domain and range of the function. 2. Determine the intercepts and asymptotes of the graph. Intermediate value theorem can be helpful for this, especially for x-intercept when you want to approximate where one may occur. Determine where f prime and f double prime, first and second derivatives, are 0 or undefined to determine relative extrema and possible points of inflection. And 4, your algebra skills will make or break you. Examples 1 through 6 in this section give good examples of how to analyze rational, radical, and polynomial and trigonometric functions. Of course, much of the work or the algebra is left out in the process of giving you key features of the graph. By now, you are supposed to know how to find that information, so that work is going to be left to you. So be sure that you read the information accompanying each example that is listed below and on the next page. There is good material in each of these small paragraphs. So some highlights from me. Okay? And each one of these deals with the graphs. So I'm going to go to the problems. Here we go. Example 1. As you can see, here's our function. We know we can factor the numerator and denominator. This will give us our roots and our vertical asymptotes, or our x-intercepts and our vertical asymptotes, but much of the rest of the work is left to you. Notice that given to you, with the expectation that you can find it yourself, are the first and second derivative, your intercepts, your asymptotes, all horizontal and vertical, critical numbers, possible points of inflection, and so forth. Why are possible points of inflection none? Go back up to the second derivative. This derivative will never be 0. So since the derivative will never be 0, there cannot possibly be a point of inflection because that will never happen, because we're squaring and then adding to it. Notice that here is our chart. It is also given for you in the textbook. And here is all of the work, including the graph. So first of all, we have our function. We can factor a 2 out of here, which will be helpful for finding the first derivative, which requires quotient rule, low d high minus high d low over low low. Simplify, there you go. I have a critical number when x is 0. This derivative will be 0 when x is 0. I get 0 on top and not 0 on bottom, so I have a critical number when x is 0. This could be a relative maximum or a relative minimum, or it might just be a place where we have a horizontal tangent. We have to keep going to find that out. Now here's our first derivative, and we're going to use this to find our second derivative. Low d high minus high. Notice that the derivative of this is going to be chain rule. 2 times x squared minus 4th to the first power times the derivative of x squared minus 4th. Okay. Over low low. You'll notice some clever math we could do is factor out 20 and x squared minus 4. And why would we do that? Because now this x squared minus 4 can cancel with one of these, leaving 3 in the denominator. And we have a little math left to do. Let's make this look a little better. Factor out the negative. And there is our beautiful second derivative. No possible point of inflection. And now we can do our analysis. The previous page showed the chart. Here we are with the lines. Remember that on my candidate test, I put my vertical asymptotes as markers on my number line. My critical number is where x is 0, and I'm going to evaluate the first and second derivative. Pick a number from negative infinity to negative 2. a number from -2 to 0, 0 to 2, and something larger than 2. And in all of these, I get, picking, say, negative 10. Negative 10 here would make the numerator negative, denominator always positive because we're squaring. So I have a negative over positive. So first derivative negative, second derivative. This part will always be positive times negative. So the numerator is always going to be negative over negative 10 squared minus 4 is positive, cubed is positive. So I get a negative. So I am going to have f is going to be decreasing and concave down, and I like to do a little sketch like that. Now, a nice convenient number from -2 to 0. How about -1? Going over here, -1 on top is going to make it negative. Denominator is positive. So first derivative negative. -1 here. The numerator is always going to be negative, but -1 down here, that's squared is 1 minus 4 is negative, cubed is negative. We have negative on top, negative on bottom, positive. So I have a f is decreasing and concave up. That's how we sketch a decreasing concave up. Notice we have a vertical asymptote at x equals -2, so I have a non-removable discontinuity. In the first derivative, let's pick x to be 1, numerator is positive, denominator will be positive because we're squaring a number, so I get positive. In the denominator, I have a negative times, again, this is always going to be positive, so the numerator is always negative in the second derivative. When x is 1, the denominator is going to be negative cubed, which is negative. So I have a negative over negative, positive. So I have an increasing concave up function. I'm picking a number larger than 2. Again, in the first derivative, we will be positive on top. And on the bottom, we will be positive. So first derivative is positive because the denominator is always positive in the first derivative. In the second derivative, the numerator is always negative. When we pick a number larger than 2, the denominator will be positive. So we are negative. So we have an increasing concave down function. And here's a graph with all of our featured points. Horizontal asymptote at y equals 2. That's our end behavior. Vertical asymptote at x equals -2 and x equals 2. My roots at -3 and 3. My y-intercept at 0 and 9/2, which is 4.5. So there you go. At the end of the notes in this section, I have a page with all of the graphs for each of the examples that are discussed. Okay. Look at my comment for this example we just discussed. All of your information goes on your chart, even the x values for which the function is undefined, since these values cause discontinuities. Okay, that is my comment for example 1. Example 2, notice there's going to be several things that come up. This problem addresses the occurrence of a slant asymptote. This is going to happen when the numerator of the function is 1 degree higher than the denominator, and there's going to be 2 ways to find a slant asymptote. If your divisor is linear, you can use synthetic division. We did that in an example in section 3.5. If the divisor is not linear, you have to use long division. And remember, the remainder portion of your slant asymptote will go to 0 as x goes to infinity, so it's not part of the line which makes your slant asymptote. And then I give further example of how to reduce something. So remember, if I'm looking at this problem here, my divisor is linear, so I can use synthetic division. What solves it is 2. The coefficients of the numerator are 1, -2, 4. They go here. You always bring this one down. 2 times 1 is 2. -2 plus 2 is 0. 2 times 0 is 0. 4 plus 0 is 4. So this reduces to this. And you can see as x goes to positive and negative infinity, this is going to be 4 over infinity or negative infinity. This is going to go to 0. So my slant asymptote is going to be the line y equals x. That's one way to do it. Here's another way to do it. Very clever way. X squared minus 2x plus 4. What if we divided that into 2 parts, x squared minus 2x over x minus 2 plus 4 over x minus 2? If I factor the x out of here, you can see that we get x times x minus 2 over x minus 2. These two can cancel, leaving our x. So again, I get x plus 4 over x minus 2. Now, just as an example for when your divisor is not linear, this is not the same problem, but just giving you an example of how to work with it. If my divisor is not linear, I have to use long division, and you have to leave a place for a missing term. Notice that the linear term in the denominator is missing, the coefficient of x, so we have to leave a place for it. Notice in the numerator, my linear term is missing, so I have to leave a place for it. So x cubed minus 2x squared plus 0x plus 3. Now, once again, my little trick is this. What do I need to multiply x squared by to get x cubed? X. Distribute the x across this entire polynomial. That's going to give me x cubed plus 0x squared minus x. Draw a line, change every sign, and add. So don't subtract, add the negative. X cubed plus a negative x cubed is 0. That drops out. Negative 2x squared plus negative 0x squared is still negative 2x squared. 0x plus x is x. 3 is going to come down because I need 3 terms to divide into. Now what do we need to multiply x squared by to get negative 2x squared? A negative 2. Negative 2 times x squared is negative 2x squared. The whole reason for doing that is to get this, so you should have done that right. Negative 2 times 0 is negative 0x, and negative 2 times negative 1 is plus 2. Draw a line, change every sign, and add. Negative 2x squared plus 2x squared drops out. Positive x minus x drops out. Positive 3 minus 2 leaves me 1. This would be my remainder. This as x goes to infinity. So I would have y equals x minus 2 plus 1 over what I was dividing by. As x goes to infinity, that goes to 0, so I don't worry about that. And here is my slant asymptote for this example. Now, I could do one other thing that's kind of crazy. I noticed that my denominator has linear factors. I could actually do synthetic if I do it sequentially and use my depressed equation. So if I start with x minus 1, what solves that is 1. Here are the coefficients of the original numerator, x cubed minus 2x squared plus 0x plus 3. Bring the 1 down. 1 times 1 is 1. Negative 2 plus 1 is negative 1. 1 times negative 1, negative 1. 0 plus negative 1, negative 1. 1 times negative 1, negative 1. 3 plus negative 1, 2. Now this is my depressed equation, and I have to use that for the next step. And for the next step, I use my other linear factor. I've already used this one. I use that one. And I use this. And this is going to drop out, so I'm not worried about it. So again, bringing down the 1. Negative 1 times 1, negative 1. Negative 1 plus negative 1, negative 2. Negative 1 times negative 2 is 2. Minus 1 plus 2 is 1. There is my slant asymptote of x minus 2. Just another way to think about doing some problems. I just discussed the main comments about example 2. But for examples 3, 4, 5, and 6, I am not going to come back to these comments. I'm going to leave them to you for you to do when you're looking at the examples. So here's our problem on example 2. Again, you can see we have a higher degree on top by 1, so we know there's going to be a slant asymptote for our end behavior. Using the proper math, we find the first and second derivative. We know there's no x-intercepts because if we go to the top and do our discriminant part of the quadratic formula, we get a negative number, so there are no x-intercepts. Our y-intercept, substitute 0 in, we get 4 over negative 2, which is 0, negative 2. Vertical asymptote, where x is 2. No horizontal asymptote because we're going to have a slant. Critical numbers, that's going to come after we find the first derivative. We're going to find that there are no possible points of inflection. Our domain, we know we have a vertical asymptote when x is 2. So we know that our domain is going to be all real numbers except for x is 2. And so our critical numbers, which we're going to find to be 0 and 4, and our vertical asymptote of 2 are going to divide all of our numbers into these intervals. Negative infinity to 0, 0 to 2, 2 to 4, and 4 to infinity. Now let's take a quick look at how we very quickly get to these derivatives. All of that work is left to you. So you should actually, in your lecture manual, do that work. So from our original problem, f prime is low d high minus high d low over low low. Simplifying gives us this. There's your critical numbers when x is 0 and when x is 4. We're going to use f prime in this form to find the second derivative. So low d high minus high d low over low low. You can see that we have a greatest common factor of 2 and x minus 2. So factoring that out will give us this. Simplifies here. This x minus 2 cancels with one of the x minus 2 factors in the denominator, and ultimately we get this for our second derivative. Now you can see why there is no point of inflection, because the numerator will never be 0. However, our concavity is changing. When x is greater than 2, the denominator will be positive, so the second derivative will be positive. When x is less than 2, the denominator will be negative. 8 over negative is negative. So I have concavity change. We just do not have a point of inflection. From pre-cal, you can do the radii. From algebra 2, you should know how to talk about domain. We had the chart given on the page here. Here is a way to do it with our number line, with the candidate test from our sign chart. And nicely, there is our graph of our function. Here's our vertical asymptote. Here's our slant asymptote that we found. Here are a relative maximum when x is 0 and a relative minimum when x is 4, and so forth. Example 3, here we have our situation with going towards positive and negative infinity with a square root in the bottom, so we know we're going to actually have two horizontal asymptotes. Again, the work is left to you to find. We want to write this here, but to find the first and second derivative, you've got to do all that work. We can see that the first derivative is never 0, so there will not be a relative maximum or minimum in this problem. We do have a place where the second derivative will be 0. That is where x is 0, so we have a possible point of inflection, and we need to see if concavity changes around that 0. So again, here is a chart you can look at, and you can do test values, something between negative infinity and 0 and positive infinity. You see the sign of the second derivative changes. So we have an increasing concave up and an increasing concave down. Again, to find those horizontal asymptotes from the previous lesson in section 3.5, as we go to negative infinity, we're going to divide everything by x squared underneath and negative x on top, and we get y equals negative 1. As we go to positive infinity, we're going to divide by x squared on bottom under the radical and positive x on top. We get y equals 1. There's your two horizontal asymptotes, a sketch of the graph, concave up, concave down. Again, read the comments on this at the beginning of the section. So here we have rational exponents, and so you're going to have to do a little bit of work to find the first derivative and second derivative. Notice that we have a place where the first derivative is 0 when x is 0 and when x is not 2, okay, but when x is 8, the cube root. So 8. So critical numbers when x is 0 and when x is 8. Possible point of inflection when x is 1. Do the test. Look at what the comments are that it says. What is very interesting about this is the second derivative is undefined while the first derivative is defined. The first derivative is defined everywhere, but the second derivative, when x is 0, the second derivative is undefined. Interesting. This is what the graph looks like for example 4. Notice it looks like that is a point, and if that were a point, the first derivative would be undefined. But the first derivative at 0 is defined. In fact, it's defined in such a way that there must be a horizontal tangent. So what would have to happen is you would have to really zoom in on that to see that it actually looks like this. So you have to be very careful with what your calculator tells you when you go to graph something. Example 5, you might want to write these down. Let us remember a difference of 2 cubes and a sum of 2 cubes. The way they factor is the linear factor is the cube root of a and b and the same sign. The rest of the factoring comes from here. Square the a, change the sign here, multiply a and b, square the b. The last term of this factor is always positive. This is how you factor sum and difference of cubes. Not the same as cubing a binomial. Cubing a binomial gives you the first term cubed plus 3 times the first one squared and the second one to the first power plus 3 times this to the first power and the second term to the second power plus the second term cubed. And if you have a minus here, you've got a cubed, and this would become a minus 3a squared b plus 3ab squared minus b cubed. That is because this is a negative sign. So when you take the negative sign with the b and put it with this here, it creates that negative sign. And the negative with the b here creates that negative sign. So you could memorize just this one formula, but remember when b is negative, the terms where you have b to an odd power will take on a negative sign. So this looks like a really nice, easy problem to do. First derivative is really simple. Second derivative is simple. Again, you have to do some aloha, but you might want to factor. And what's nice about this is if you factor out an x, it leaves this, which you could try factoring by grouping, but it actually follows into this pattern up here. Okay. So this factors into the remainder here, into x minus 4, the quantity cubed. And you would probably want to actually find your first and second derivative from this form because you will be able to factor out some common factors to make this nice and simple. Let's remember, we are going to want our first and second derivatives to be factored as much as possible because we're going to want to know where they're 0 or undefined for our critical numbers and our possible points of inflection. Again, I leave all the work to you. Look at the comments and the graph later. Here is a trigonometric function. We know that cosine is continuous, 1 plus sine. This is going to be continuous except for where we have values that will give us 0 in the denominator. We're going to get a 0 in the denominator when sine of x is negative 1. And that happens at 3 pi over 2. So that gives us a vertical asymptote there. Now, let's look at first and second derivative. You will notice first and second derivative, again, the denominator is going to be undefined when x is 3 pi over 2. This is never going to be 0. Let's look at the second derivative. The second derivative will be undefined when x is 3 pi over 2, but when will it be 0? This will be 0 when x is pi over 2, because that's where cosine is 0. So we have a possible point of inflection at x equals pi over 2. We have no time where the first derivative is 0. So again, here's your chart. There's your graph. Be sure to go back and look at the comments on examples 5 and 6. Your TPs are numbers 5, 7, and 9. See you next time. You have a lot of work to do. Be sure you get it done.